Hi, my name is Mehmet İlter Arıkan, and welcome to my Physics 102 project. Today we are looking at the fundamental laws of capacitance and the conservation of charge. In a perfect theoretical physics problem, a charged capacitor isolated from the power source traps its electrons forever. But in a real-world engineering environment, things get a lot more complicated. Let me show you what happens when we manipulate the physical space inside the capacitor. As a disclaimer, the videos that are about to be shown about the capacitors are filmed for demonstration purposes and isn't the videos used for finding the experimental data. For this experiment, I built a parallel plate capacitor using two 10 by 10 cm aluminum foil plates. I connected them to a 10 volt DC power supply, allowed them to fully charge, and then completely disconnected the power. At this exact moment, a specific amount of charge, Q, is trapped inside the plates. According to the formula, C equals epsilon A over D, if I increase the distance between the plates by adding thicker layers of insulating paper from 0.3 mm up to 0.7 mm, the overall capacitance has to decrease. And because our trapped charge is a conserved constant, a drop in capacitance means the voltage must mathematically spike to compensate. That is the theory, but here is the reality about laboratory equipment. To measure this voltage spike accurately, you need an electrometer, a device with near infinite internal resistance. Due to lab limitations, I had to use a standard digital voltmeter, which only has about 10 megaohms of resistance. In physics, the act of observing a system often alters it. The moment the voltmeter probes touched the isolated plates, it created an closed RC circuit. The voltmeter wasn't just measuring the trapped charge, it was draining it. The voltage reading began dropping almost instantly. To bypass this instrument error, I recorded the voltmeter screen on video. By analyzing the footage frame by frame, I was able to capture the absolute peak voltage at the exact millisecond of contact, right before the rapid discharge began.